Yes, indeed, today I would like to present some small overview of our recent progress and basically discuss what can we tune under the high frequency regime of the driving, what material parameters and properties. And as we discussed many times during this workshop, that's important to be able to control material properties, because sometimes material lies very close to the interesting phase, but not yet there. So then the change of the interaction or the hopping parameters will allow us to explore and undergo the phase transition towards this interesting phase, and also maybe explore some unusual phases that we can access only out of equilibrium. And this control can be done in many ways. For example, changing the temperature doping, as shows the famous phase diagram of cuprates. Also, many system parameters can be controlled dynamically, and what is even more important, reversibly, applying magnetic and electric fields. And of course, we always have the possibility to physically change the distance between atoms, applying strain and pressure. And in this case, we can undergo the phase transition from a metal to the insulator and back. And today I will be focused on the application of laser fields. And basically this slide shows the overview of what I will discuss today. When we irradiate the material, of course, we can excite many different collective excitations. And then under the high frequency regime of the driving, there is a possibility to control all of them. Also, since the electronic spin is a property of electrons, by tuning the properties of electrons, we can control magnetism, and also we can explore the very interesting topic of light-induced topology. And during this workshop, we learned that we can very nicely describe material properties using complicated numerical calculations. However, I will just like to make one step back and introduce some very simple analytical approach. Maybe it's not very precise in describing real properties, but at the same time, it allows to have an exact and explicit dependence of system parameters on the applied perturbation. So then we have a clear idea of what and how we can tune the interaction and hopping parameters in the system, and what does it lead to. And this formalism is a Flaquet formalism, and I will discuss the precisely Magnus-like expansion introduced in these two works. And the main idea of the Flaquet formalism is to describe a non-equilibrium steady state of the system, meaning that the time-dependent Hamiltonian will be effectively replaced by the time-independent Hamiltonian that describes the dynamics of the system averaged over the period of the driving. For that, we just start with the usual Hamiltonian that contains the kinetic and interaction part. And since we will be focused on the latest problems, the kinetic part is just the hopping of electrons. Here we can have different band indices, spin indices in the case of spin-orbit coupling, and so on. And again, time dependence here is accounted for by the parallel substitution. And finally, we can write the usual Schrödinger equation, where I introduce the small parameter that compares the frequency of the driving and the typical energy scale of the system. So that we have a small parameter alpha, and my Hamiltonian is now rescaled by the same energy scale. Then what we can do, we can introduce a unitary transformation in the following form, where delta is a time-dependent periodic function that can be also expressed in powers of the small parameter. And finally, we can arrive in at the new Schrödinger equation, where now we have an effective Hamiltonian, which is time independent. So the main idea is that our delta will exclude the time dependence at the considerate order of perturbation. And how to do that? The explicit form of this time independent Hamiltonian is following. here we have a partial derivative of the time of the exponent, and using the well-known expression, we get a bit complicated form, which involves the commutator of commutator of commutator, depending on the order we want to describe. And then, of course, the time-independent Hamiltonian can also be written as the perturbation expansion, and collecting all powers of the small parameter, we can truncate the series and describe the effective problem up to the order we are interested in. So then the zeroth order contribution, as I already mentioned, will be just the time average. And to see that, the zeroth order contribution is given by the very simple formula, where we can make the Fourier transform and gather all time-dependent terms here. And then we can say that, or we can claim that our delta will exclude the time-dependent part of this expression, and we end up only at the time-independent term, which is given by the time average. But keeping in mind that in our case, the time dependence comes only from the kinetic part of the Hamiltonian, then we can take basically the average, and this average will renormalize only over the hopping amplitude. And looking at the exact expression, our hopping now is renormalized by the Bessel function of the zeroth order, and A is the amplitude of the field, and the zeroth order Bessel function at zero field is unity, and then increasing the field it reduces. So basically our hopping amplitude under the perturbation is reduced, and then this reduction of the hopping amplitude compared to the Coulomb interaction already can explain the metal to mode insulator phase transition in single band systems. But of course, if we have multi-band systems, all hoppings are renormalized in a different way, and this can be seen from the following example. If we look at the band insulator, in our case it was single layer black phosphorus or phosphorane, and looking from the top view, the phosphorine reminds very well the graphene. So we have the hexagonal or honeycomb lattice structure, but from the side view, the system is buckled, so that the minimal unit cell contains 4 atoms instead of 2. And then tie binding model was introduced by Alexander Rudenko in the following paper. And then applying the light and all this machinery I just explained, we can see that indeed we start from the band insulator. Here I plot lowest 2 bands, and then by increasing the field, we find that the bands touch at gamma point, and then the gap can be closed. But later, when we increase the field, the touching point creates 2 Dirac points that move from the center, from gamma point, to the corner of the Brillouin zone. Then it moves back, and then the gap can be reopened again. And this we find for the linearly polarized light. But the most exciting part comes when we apply the circularly polarized light, because then the system can undergo the Lifshitz transition to a topological insulating state. And this is clearly seen in this figure, where we plot 4 bands at gamma point as a function of the applied light. And the structure of the system allows the touching or the closing of the gap only at the gamma point. So then we can see that we can plot the band structure at the field 2.8 before the closing of the gap and right after. And here we just considered the nanoribbon because we wanted to focus and to have boundary modes to explicitly show that we have a topological state. And then before the closing of the gap, we have indeed just a band insulator. But after that, we see that when valence and conducting bands, they close, and then we get a band inversion. We have also surface, or in here, in this case, it's not surface, it's boundary modes that connect valence and conducting bands. So indeed, we have now the dynamical version of the Haldane model. But this story was about the non-interacting system, and then, of course, everything relies on the change of the hopping amplitude. Now, let me investigate, can we tune also the interactions? Because in this case, we can also access the control of magnetism and also collective excitations. And for that, I will start with our usual toy example, extended Hubbard model, where I consider hopping amplitude, spin orbit coupling, local and non-local Coulomb interactions, and also I will consider the direct spin-spin interaction, which for our case connected to magnetism will be very, very important. And as we discussed at the zeroth order, only the hopping amplitude gets renormalized. And in this case, if we introduce a spin orbit coupling, the spin orbit coupling is also renormalized by the same Basel function. Then, if we consider single band systems, the first order correction in the small parameter doesn't introduce any new terms, but already the second order correction additionally induce the correction to the local Coulomb interaction, non-local Coulomb interaction, and spin-spin interaction. And of course, there is another very interesting term that appears. It didn't exist in the initial Hamiltonian, however, now we have it. And this is the hopping of doublons. So basically, two hopping process when we create two electrons on the same site and destroy them at another site. But these corrections are of the second order, and that's why they appear with a prefactor lambda square and also 2t square over u, which means that this is a very small correction for Coulomb interactions. But of course, we know that in the case when we have a strong interaction, the spin-spin interaction is of the same order. And of course, if we didn't have the doublon processes in the initial system, this term will also be important. So we will focus on these two parts. So already the system and this analytical theory suggests that for some interesting effects, we rather have to look not at the electronic properties, but rather at magnetism and doublons. And first, let me discuss the magnetic part. And when doing the Schrieffer-Wolff transformation, we arrive at the spin Hamiltonian. And here I will explicitly distinguish the nearest neighbor exchange interaction between spins next to nearest neighbor interaction. Also, the Lashinsky-Mori interaction that comes from the fact that we have a spin orbit coupling in the system. And in principle, we can also have a magnetic field. And what is mostly discussed about spin Hamiltonians nowadays are different spin structures, and in particular, topological spin structures such as skyrmions. And the skyrmions can be identified calculating the winding number that counts how many times the spin of the structure winds around the unit sphere. And of course, nowadays, this topological spin structure is studied in the context of memory devices and so on. But unfortunately, not in many systems, these structures can be stabilized because it requires usually skyrmions, they appear as a competition because of magnetic frustration, and in this case, they can appear as a competition between nearest neighbor, for example, ferromagnetic, and next to nearest neighbor spin-spin anti-ferromagnetic interaction, or the exchange interaction in the Lashinsky-Mori interaction, and so on. But in many systems, the skyrmion is not the ground state, and for stabilization, it requires the non-zero magnetic field, which means the control of system parameters will allow us to have skyrmions in materials where they do not exist in the equilibrium situation. And to illustrate that, we can, doing the same machinery I explained, we can have the explicit expression for the exchange interaction that after the Schrieffer-Wolff transformation is the combined effect of the direct exchange interaction that we had in the system from the very beginning, and also the induced correction to that, and the kinetic exchange interaction, which is antiferromagnetic and is indeed 2t squared over u. And since the hopping amplitude was renormalized by the Bessel function, this Bessel function squared appears here. And the explicit forms of the induced correction is following, where m here larger than 0 is a Bessel function of the m's order. And as I discussed previously, the Bessel function of the zeroth order starts from unity and decreases, but the m's order larger than 0 starts from 0, and increasing the field, the Bessel function increases, which means that we have a natural competition between the direct ferromagnetic exchange and kinetic antiferromagnetic exchange interaction here. And at some point, the interaction can change sign, and this was also discussed in the following work. But if we introduce the spin orbit coupling in our system, the Dzielaszynski-Mori interaction is given by a very simple formula, and the light does not induce any correction to Dzielaszynski-Mori interaction. And also, when we discuss these effects, we always have to keep in mind some realistic systems where we can test the theory. And for our case, it's very important, as I previously mentioned, to have non-zero exchange interaction between spins. And this was found in effective 2D materials, systems of atoms on top of silicon or graphene. And calculating the exchange interaction for such systems, we find that indeed the exchange interaction starting from the antiferromagnetic phase at some point can change sign and become ferromagnetic. And this, of course, happens with the help of the direct exchange term, because without the direct exchange term, this transition comes very late at very high fields. So it would be quite unrealistic. And also, if we consider now nearest neighbor and next to neighbor hoppings, then we get nearest neighbor and next to nearest neighbor exchange interactions, and we can find that in principle, this exchange change sign at different fields. So we indeed can have a situation where the nearest neighbor interaction already changed sign, and next to nearest not yet. And as expected, the Dzielaszynski-Mori interaction doesn't change sign because we have a squared Bessel function here. And finally, we can plot the ratio between the exchange interaction and Dzielaszynski-Mori interaction, which approximates the radius of the skyrmion. And we indeed find that close to the phase transition, we can have very small skyrmions that will be very easy to stabilize. And to illustrate that, the magnetic field on the phase diagram I introduced previously, the stabilization magnetic field is proportional to the exchange interaction. So then before the phase transition, when we have a very small exchange interaction, the stabilization field is also reduced. Another problem comes when we have ferromagnetic skyrmions, because in principle, the range of magnetic field is not very broad for stabilization. And if we instead go now from the antiferromagnetic phase and undergo the phase transition to the ferromagnetic state, we can indeed, at very small radius of the skyrmion, have a very broad range of magnetic field that helps stabilization. Then we can also, here I have a misprint, this is J3. We can investigate the case of frustrated magnetic lattice without Dzielaszynski-Mori interaction, where skyrmions appear as a competition between nearest and next to nearest neighbor exchange interactions. The following ratio for G1, G2, and G1, G3 was obtained in the work by Akuba. And indeed, for our considered systems, we can find a range of fields where the transition to the stable skyrmion state is possible. And to close this topic, we realized that not only the size of skyrmions, but also the shape can be tuned. This was firstly demonstrated in the following paper, where the circle skyrmions were turned to elliptic ones, applying the strain. But it's known that the high frequency light always works as an effective strain field, and this can be easily seen when calculating the exchange interaction in the Zieloszynski-Moria. And if we look at only the kinetic exchange, we find that together with Zieloszynski-Moria, it is renormalized by the same Bessel function. So even if we apply different polarization of the field, the skyrmions cannot be turned to the elliptic form. However, if we now have the direct ferromagnetic exchange interaction, which is also induced by light, but the main contribution, of course, comes from the initial term, we indeed can have elliptic skyrmions. And then I still have a bit of time, so I can discuss our last project that describes how we can control collective excitations. And by doing the Schrieffer-Wolff transformation together with spin-spin interaction, we can also have the doublon-doublon hopping and doublon-doublon interaction terms. As you remember, this term, the hopping of doublons, was already induced by light up to this, when we consider the expansion up to the second order. But here, when we introduce the Schrieffer-Wolff transformation, we can also have 2t square over u contribution for that. And then the hopping of doublons at the first or the zeroth order of expansion and the doublon-doublon interaction are again renormalized by the same Bessel function. So it's not very interesting because it only rescales the parameters of the system in the same way. However, if we go to the second order of expansion, we find that the corrections to the main contributions are very similar, except the -1 in power of m prefactor, which results in a quite different behavior as a function of the field, which is shown in the plot. So we see that the hopping of doublons increasing the field doesn't change sign, while the doublon-doublon interaction can change sign. And this is also illustrated for different frequencies in the inset, and parameters of our model here is the hopping equal to 1, which is the energy scale, and the Coulomb interaction is 3. Fine, but the problem is that the doublon-doublon interaction cannot be detected in experiments because when we usually want to describe or detect the interaction, we have to measure two-particle correlation function. But the two-particle correlation function for doublons means that it is 4-particle correlation function for electrons. However, this change of sign can still be measured in experiments, and also in a very efficient way through the density of states, which can routinely measured in many experiments. And to illustrate that, we can investigate the density of states. And now this density of states was calculated by Victor van Mispild via the non-equilibrium DMFT. And what we can see that in this parameter range, when we drive the system in the high frequency regime, of course, the hopping amplitude is reduced. And then for our considered range of fields, we are in the Mott insulating regime, which shows 2 Hubbard subbands here. But Hubbard subbands, to some extent, are really like doublons and holons because they describe fully occupied and fully unoccupied lattice sites. And then changing the value of the field, we observe that Hubbard subbands, they start to move. They move close to each other, and then they repel and come to plus minus u positions back. And we know that position of the Hubbard subbands are described by the local Coulomb interaction, just simply diagonalizing exactly the local part of our Hamiltonian. And of course, it's not surprising that the position of Hubbard subbands is changed, because we get the induced correction to the local Coulomb interaction induced by light. However, when we start to investigate that, we realize that alone this local Coulomb interaction, or the change of this local Coulomb interaction, cannot explain the change of the position of Hubbard subbands. And then, of course, we know that in the initial Hamiltonian, we have hopping processes. We can, of course, have non-local Coulomb interaction. And then all of them, they effectively affect the local Coulomb interaction. And in the work by Malte-Schuler and others, it was shown that in principle, extended Hubbard model with the non-local Coulomb interaction can be mapped onto the Hubbard model, where the only on-site Coulomb term exists. And the effective mapping in our case, of course, is the effective local Coulomb interaction is local Coulomb minus the nearest neighbor Coulomb interaction. However, we can also introduce the Landau free energy and find that double hopping processes also affect the local Coulomb interaction, which gives the following correction that involves the double occupancy of in the -1 form as the correction to the local Coulomb interaction. And finally, if we indeed plot this result, we find that our analytical curve, the solid line, matches quite well points that show the DMFT result. And this is the position of the upper Hubbard subband, which is the following. And this is very interesting, because when we don't have the population inversion in the system, the largest value of the double occupancy is 0.25 at half filling. And then if we substitute the value of the double occupancy here at the maximum one, we find that this expression, or the delta, which shows the difference of the position of the upper Hubbard subband with respect to the half of u, is exactly 2 times the interaction between doublons, which means that in the realistic case, when the double occupancy, of course, is smaller than the 0.25, we have that this change of the position is strongly larger than twice the interaction, which means that when the delta change sign in these regimes, the interaction between doublon has to change sign, which is indicated by the perpendicular dashed lines. So in this case, we of course can detect the change of the interaction, which is of course very helpful, because doublons are bosons. So then by this change of the interaction, we can dynamically control the Bose-Einstein condensation of them. And with this, I would like to thank you for your attention with a small summary of our project. Thank you.